Okay, we're going to talk about section 11.2. 11.2 deals with chi-squared two-way tests, as we call them. They deal with a situation where we're going to have, in essence, a matrix that we're going to work with. But let's talk about those. We have two kinds of tests that we're going to do in this section. And of course, in chi-squared, we aren't doing any confidence intervals. We just, in section 1, we have the goodness of fit test. And then we have two types of tests, and they're very similar, and the mechanics of these are done basically in the exact same way. But the differences in these two things are the sampling method and kind of the terminology that goes with them. So the first one we're going to talk about is a chi-square test of homogeneity of populations, or you could just call it a test of homogeneity. It is based upon you are going to have two populations in the problem. Two populations, and thus you're going to have two samples that are going to compare one variable within those samples. Compare one variable. So it'll be something like, and of course these variables have to be categorical. It'll be, is there a difference between the people of Mississippi and the people of Alabama in regards to some categorical variables, such as their political party affiliation or their religious affiliation, something like that. But you're going to have two different populations and two samples. And the big word that's going to come up is there a difference? That frequently is going to be kind of the giveaway word for a test of homogeneity. Is there a difference in these two populations in regards to a categorical variable? And once again, it cannot be quantitative. It can't be something like height or weight or something that's listed in a quantitative way. And so that's the first kind of test that we're going to look at an example for. And the other way of saying chi-squared is that, the Greek letter chi. So a chi-squared test of association independence, or you could just call it a chi-squared test of independence, and that's going to be our second example. And it's done in a really similar sort of way as you're going to see. But the key thing is, the big difference is there is just going to be one sample, in essence, one population, all right? But there's going to be two variables. And what it's going to ask is there a relationship between these two variables? So it'll say, amongst this group of people, is there a relationship between two categorical variables, such as, is there a relationship between race and political party affiliation? Or, the way of wording it, like on this other problem I said with Alabama and Mississippi, is that it could word it, say we took one sample, is there a relationship between what state people are from and their political party affiliation? Something like that. But the key thing that you would need to notice is just one sample, and it's asking, is there a relationship between the two variables? So that is sort of a key word. Or another thing it could be, it could say, is there an association, between, let's say political party affiliation and what religion people are, or what colors the flowers are and what state they're in. It has to be, or is there a relationship? Is there an association, or are they independent? Would be another key word that could be in the problem to identify this. Are these two variables independent? In which case, it's going to be the second one. Now, and so let's look at a couple of examples of what I'm talking about here. And of course, part of this is going to be a little bit of a review of chapter 1. So first of all, we're going to do a chi-squared test of homogeneity of populations, where we're going to have two different populations, or we're going to be asked to compare a categorical variable between these two populations. So it says, a researcher wishes to see if there's a difference in the male and female adults in her city in regards to their political party affiliation. She takes an SRS of 60 males in the city and finds that 40 are Republicans, 10 are Democrats, and 10 are other political affiliations. She takes another SRS, so that's two different SRSs, so that's a clue, it's for homogeneity, and finds that 10 of them are Republican, 20 are Democrats, and 10 are other. Draw an appropriate graph to compare the males and females and perform an appropriate test. And so, all right, so we're dealing a situation here where we have two different populations. two different samples. And so we were asked to, are these two populations different, or homogeneous means are they the same in essence? And so anyway, now first thing I want to do, most of the time the data in these problems is given in the form of a two-way table. So let's just list this in a two-way table. So we have males and we have females in this city. Those are our two populations, the males and the females. And so we have some that are Republicans, some that are Democrats, and some that are other political affiliations. So we've got 40 male Republicans, we've got Democrats, we've got 10, and we've got 10 other. And then for the females, we've got 10 Republicans, we've got 20 Democrats, and we've got 10 other. Okay, and so we're asked to make a graph. Now, we encountered this situation in chapter 1 where we had categorical data and we're asked to make it a graph. And so the graph we're going to make is a bar graph. And we got two variables, so we'll make a side-by-side bar graph. And so in order to do that, I need the marginal distribution. So we have a total of 60 males here, and we've got a total of 40 females. And then total number of Republicans, we have 50 Republicans, we've got 30 Democrats, and we've got 20 other. And so now in order to make a proper bar graph, we need the conditional distribution. In other words, we need percents because we have different numbers of males and females. And so if we want to compare them, we need to know the percents. And so you could do it by row or by column, but I'll do it in essence by row here. I want to know the percent of males that are Republican. And so I'll say, well, that would be 40 over 60, and so that's going to be 2/3, which is 0.6 repeating. All right, and then 10 over 60, so that would be 0.16 repeating. So about 17% of the males are Democrats, and then 10 divided by 60, 0.16 repeating. So about 17% of the males are other. And similarly with females, 10 out of the 40, so 25%, 0.25 of the females in this sample are Republicans. For Democrats, 20 out of 40, which is 50%, and then 10 out of 40, 25% of the females are or other political party affiliation. So, of course, you could have done it by column like this. The percent of Republicans that are male would be 80%, and so 20% for the females. But this is just the way I chose to do it. So we'll make a bar graph. And so to make our bar graph, I'll go, well, the y-axis is going to be percent, the percent of the people. And then we'll say, okay, first of all, I'll just put Republican, Democrat, and other down here. And so the highest percent I'm going up to is 2/3. So I'll just go 10, 20, 30, 40, 50, 60, 70. So that's 70% and 50 and 30 and 10. Trying to do this as neat as I can, but and I'll just I will make a little open circle. I'll say that's the males, and then the filled in part will be for the females. And so for the Republicans, it's 2/3. So I go up to about there, to 67%, and then for the females, a Republican is 25%, so that would go to about there. And then for the Democrats, for the males, that'd go up to about 17%, something like that. And the females would go all the way up to 50%. So there we go. And then lastly, for the males, once again, is 17%, and the females 25%, a little bit more than that. And so there we go. And so remember in chapter 1, we don't cuss when we're describing categorical data. We just describe what we see in the bar graph. And so we would say, well, for the males, they're much more likely to be Republican, and the females are much more likely to be Democrat or possibly other. And so there you go. And so that is in essence drawing the graph, which we did in chapter 1. Now let's do the test. It says perform an appropriate test. And so what we want to know is, in essence, is there a difference in the males and females in their political party affiliations? Certainly in this sample there is, as we just said, but is it statistically significant? In other words, is it beyond what we would expect due to sampling variability? There's certainly a much higher percentage of males that are Republicans, a much higher percentage of females in this group that are Democrats, but can we definitively sort of say, hey, we've got really strong evidence that that's going to be true in the population. And so this is what is known as a chi-squared test. And so, of course, we're doing a test here. And so we would go through our THAME acronym as we always do. So our type of inference that we are calling here. So this is a chi-squared test of homogeneity of populations. Okay, because we've got two different populations, and we're comparing a categorical variable. So that is what we call this situation. So we are asking the question, are these two populations different? All right, so that's so make sure and memorize that name. All right, now our hypotheses. All right, in a chi-squared test of homogeneity, your null hypothesis is always going to be that there's no difference in the populations in regards to this variable we're measuring. So it'll be the same in essence. So our null hypothesis is going to be there is no difference. There is no difference in the males and females of this city in regards to political party affiliation. Political party affiliation. Now, the alternative is going to be that there is a difference. There is a difference. You can certainly use ditto marks here. That's perfectly fine. Try to write it maybe a little bit neater than I did there. City in regards to political party affiliation. So there's your, so that's in essence always going to be your null and alternative hypothesis. Then we have our assumptions. We have to verify our assumptions or our conditions. So our assumptions, we must verify them. In other words, state whether or not we think they're true in this situation. And now we're back we have two different samples here. So these samples have to be independent. So we're going with the ISIN, but of course with chi-squared, we don't check for normality. So we're leaving out it's the expected counts. And so what we would say here, it clearly says up here SRSs were taken, and there's no reason to believe they were influencing each other. They were done independently. And so we can say this, it says SRSs were taken, thus independent. Random condition is met. Random condition is met. Okay? Whenever you have two samples, you have to use independent random. Or it could be, that you have random assignment to treatments in an experiment. That would be the other thing that can happen, in which case you would say, the independent random condition is met for people or animals or things that are like these, so to speak. And then our population sizes have to be at least 10 times our sample sizes. So I'm not going to, so there must be, I won't write it all out, but there must be, maybe I will write it all out. There must be at least 600 males and 400 females in this city for our population sizes to be at least 10 times our sample sizes, because we're not using replacement. So our population has to be big enough to where using replacement is affecting it significantly. And then the last condition, don't say normality in this chapter. All right, it's the expected counts. Expected counts have to be greater than or equal to 5. And you just have to show what the expected counts are. And I'm just going to say shown below. You have to show them. Frequently, they'll be shown above in a table or something, but I'm going to show them in a table down below. A lot of times they're given to you, but so now we've got to calculate the expected counts. Of course, I'm going to need them in my mechanics anyway. All right, so now let's talk about, and so now we go to our mechanics, and so we're going to talk about our test statistic and our p-value. And so let's talk about that. Now our test statistic, as we talked about in section 1 is this guy here. The chi-squared test statistic, it's the last formula in your formula sheet. It is the sum of the observed values minus the expected squared over the expected. Okay, so we will write this out. So this would be our chi-squared is going to be equal to the observed values minus the expected value squared over the expected. Well, let me write out our observed values again from our sample. So our observed values are, so we have males and we have females, and so we have Republican, we have Democrat, and we have other. And so this would be 40, 10, and 10. This would be 10 and 20 and 10. And so once again, our marginal distribution is we've got 50 total Republicans, we've got 30 total Democrats, we got 20 other. And so there was, in our two samples together, we got 100. We had a total of 60 males, and we got a total of 40 females. All right, and so those are our observed counts. Those are our observed values. Now, to find the expected is this, and our little formula is going to be this. And hopefully this will make intuitive sense after I explain this. Our expected counts, or our expected values for each cell is going to be equal to the row total times the column total, over the table total. Now, let's think about this. For instance, if the null hypothesis is true, and the null hypothesis is basically saying that males and females are the same in regards to political party affiliation. Well, if the null hypothesis is true and they're the same, the total number for both samples for Republicans is 50 out of 100. Okay, so in other words, half of the people here are Republican, 50 out of 100. Well, if the null is true, that means that for both the males and the females, 50 out of 100 of them, or half of them, would be Republican. And so if that is true, if you take 60 males, well, we're expecting half of them, 30, to be a Republican. And that would be the expected value. And so for the females, you would say, well, if half of them are Republican, that means I would expect 20 of them. So if the null was true, and there is no difference in the males and females, we're expecting the males and females to be the same. And so 50 out of the 100 of these people, it ought to be the same for both the males and females. Half of them would be Republican. And also 30% would be Democrats, all right? Because we've got 30 out of 100 that are Democrats in the combination of these two samples. So that means for the males, we're expecting 30%, which that would be 60 times 30 over 100. And that is, in fact, equal to 18. So I'm putting the expected counts in parentheses here. And so similarly for the females, if the null is true, so we're expecting 30% Democrats, well, 30% of 40, so that would be 0.3 times 40, and that would be 12. And that's also using this formula up here. In other words, like for this cell, the expected count is just going to be the row total times the column total over the table total. So 30 times 40 is 1,200, divided by 100 is 12. And then similarly, we're expecting 20% of both of them. If the null is true, we're expecting 20% to be other affiliation, so 20% of the 60. And so that is going to be 12 for the males, and then 20% of the 40 would be 8 of the females. And so that is how you get the expected counts. Now, yes, your calculator is going to have a little shortcut to this. Now, to calculate your chi-squared test statistic by hand, you would have to do this formula for this cell. You'd have to, for each of these 6 cells. And so to calculate your chi-squared, you would say, okay, chi-squared is equal to, and so you would say, first of all, for the male Republicans, it would be 40 minus 30 squared over the expected 30. That's our little formula. And so when you calculate that, in fact, that is going to equal to 3.3 repeating. That is how much that this cell, the male Republicans, contribute to our chi-square. Plus, now we do it for the Republican females. And so that is going to be the observed 10 minus 20 squared over 20. And that, in fact, is equal to 5. Okay, and you would keep going on. You would do it for, the Democrat males. 10 minus 18 squared over 18. That, in fact, is equal to 3.5 repeating. What the heck, we'll do it for all of them. 20, and then we would say plus, and then down here, 20 minus 12 squared over 12. And then plus 10 minus 12 squared over 12. And then plus, and that would be 10 minus 8 squared over 8. This, in fact, is equal to, I believe, 5.3 repeating. And that is equal to 0.3 repeating, and that is equal to 0.5 plus 0.5. When you add all of those up, they equal to 18.05 repeating. That is our chi-squared test statistic, and that is how you calculate it by hand. The next question is, the next number you have to find in regards is the degrees of freedom, which identifies which chi-squared distribution we're working with. The degrees of freedom in section 11.2, when you have a two-way table like this, it's equal to the row total minus 1 times the column total minus 1. The column total minus 1. So in this case, there's 3 rows. So that would be 3 minus 1. And 2 columns. So that would be 2 minus 1. And so that's going to be 2 times 1. There's 2 degrees of freedom. That tells us which chi-squared distribution we're working with. So that's the second number you have to write. And yes, when you do the little shortcut with your calculator, it's going to tell you that. Now we need to find our p-value. And if we were using our table, this is what we would do. So we would go to our chi-squared, our table C, which is given to us, our 2 degrees of freedom. So in this case, our chi-squared is equal to 18. And so when you look, degrees of freedom, each row is a different chi-squared distribution, and our p-value is going to be the area outside of our chi-squared value. So when you go to 2 degrees of freedom, and our chi-squared test statistic is 8 over 18, you would realize 2 degrees of freedom, you would go across, our chi-squared value is off the table. The biggest one here is 15.2 in this row. And so in other words, the p-value would be below that. And so we would say that. We would say, our p-value is less than 0.0005. And so we would reject the null in favor of the alternative because of the low p-value. Now, the other way, as we discussed in the last section, is to find a p-value is with chi-squared CDF. So we could say chi-squared CDF, and with chi-squared, it's always, since we square it, your chi-squared value is always positive, so the p-value is always the area bigger than that. It's always bigger than that. And so it'd be chi-squared CDF of 18.05 repeating. That is my lower bound. My upper bound is infinity, and then my degrees of freedom is equal to 2. And so that would be, in essence, showing your work in that regard. All right, now chi-squared, remember, CDF, it's right near normal CDF. You go second distribution, and you go down to chi-squared. There it is, chi-squared CDF. And so we would say 18.055556, let's say, and to infinity. 1e, 99 degrees of freedom 2, and so we'll hit that, we go with that, and sure enough, a very small p-value, 1.20 times 10 to the negative 4th. So 1.20 times 10 to the negative 4th is our p-value. So in other words, really effectively 0. And then we would draw our conclusion. So our conclusion that we would draw from that p-value, just like what we've done before, we would say this p-value is less than 0.05. Thus I reject the null hypothesis. Thus I have convincing evidence that, and then you restate the alternative. I have convincing evidence that there is a difference in the males and females in this city. that in regards to political party affiliation, that there is a difference in the males and females in this city in regards to their political party affiliation. Of course, write that out neatly. So, okay, that is how you do it. Now, let me show you the shortcut with your calculator. Yes, in your mechanics, you just have to write down these three numbers that I circled. Okay, and do you need to understand what I did up here in regards to the expected counts and in regards to, yes, you do. But this is all you have to write down when you're just doing a test, okay? This is the sort of question that can come up in a multiple choice sort of question. I guess the other thing that could be asked, and we talked about this last time, is the components of chi-squared. Is the follow-up analysis. So if you were asked to do a follow-up analysis, you just want to comment on which cell contributes most to the chi-squared. And you would look at these and you would say, okay, here's the components of chi-squared. Okay, it is the sum of these 6 numbers. And so when you look at it, so this number, well, that was the cell that went with the female Republicans. So they contributed 5. So they contributed a lot. But also this cell, and this cell was, let's see, it's the 4th cell, so I believe it was the female Democrats. It contributed the most at 5.3 repeating. So if you were doing follow-up analysis on this, you would say, well, those two contributed the most. But all right, let me show you how to do the shortcut with your calculator. So what we're going to do is this: we're going to put our observed counts in a matrix. And so this is something that is new to us this year. So the matrix menu is right there. It's right below the math button, right above the X to the -1 button there. And so this is what we'll do. So we're going to do second and hit matrix. And so then what we're going to do is we're going to go over to edit matrix. So we'll edit our matrix. Okay. Now, in this case, we have 3 rows and 2 columns. So I'm going to say 3, enter, 2, enter. So I go 3 by 2, and then you just enter the numbers here. You go 40, enter, and of course I had already entered this in, 10, enter, and then 10, enter, and then 20, enter, 10, enter, and 10, enter. So there we go. So I've entered the matrix. Now what I'm going to do is I'm going to go do the chi-square test. So now I'm going to hit the stat button, and I go tests, and you scroll down to the chi-square test. There. That is the section 11.2. That's, of course, goodness of fit. That works with lists like we did in section 1. So there's the chi-squared two-way test, in essence, as it is called. And so I hit enter. So matrix A. If it didn't say matrix A there, it should. But if it didn't, then you could put matrix A by just going second matrix and then just hit enter on A. And it'll put matrix A there and then put matrix B there. That is where it's going to store the expected counts. You don't have to store the calculator is going to calculate the expected counts for you. So everything I just showed you in this right here, your calculator is going to do it for you. But you have to understand what your calculator is doing. So we go down and we calculate, and there is my test statistic, p-value, and my degrees of freedom. And those are the 3 numbers that you have to write down in your mechanics. So that is how you do a chi-square two-way test. All right, so now let's do this for our other example is when we have this guy here. So that is a chi-square test of association independence. It is a very similar thing. These problems are going to look very similar. Most of the time, you're going to be given a matrix that looks like this. It's going to have numbers like this. And you notice, well, it appears to be categorical data. Categorical data means chi-squared, and we have a two-way table. So it's either going to be a test of homogeneity or a test of association independence. How can you tell the difference? Test of a homogeneity has 2 samples. 2 samples. Whereas a test of association of independence has 1 sample, but 2 variables that it's asking to compare. And test of homogeneity is going to ask, is there a difference? Is there a difference between these two? Which actually, that word, does that come up here? But yeah, is there a difference? That's the key word to look for if it's homogeneity. But in the test of association and independence, it's going to say, is there an association? Is there independence? Or is there a relationship? That would be sort of a giveaway word. And the fact that there's one sample, two variables. So let's do this problem. An educational administrator would see if there's a relationship between how advanced the student is and his or her opinion about whether or not the school should have stricter discipline policy. He takes a random sample, just one random sample of 89 students and gets the results. So it's one random sample, two categorical variables. They've been categorized in regards to low level, average level, advanced level. It didn't like use some sort of quantitative thing like a specific test score, but it categorized them. So this is going to be a chi-squared test of independence, otherwise known as a chi-squared test of association. But anyway, perform an appropriate test. So to test two categorical variables like this, so our type of inference is going to be a chi-squared. Don't say x squared. That is a chi-squared. A chi-squared test of independence. You could just call it that. Let's say it's, or you could call it a chi-squared test of association. Or so there you go. So now our hypotheses. So our hypotheses, our null hypothesis is always going to be that there is no relationship between the two variables. Okay, there is no relationship. There is no relationship between our two variables. So in this case, it's level of student, and opinion, I misspelled opinion, on discipline, let's say. And of course, where did our population here, where did they get a random sample of the students? So, and so this would be at this school. So whether or not the school should, okay, so it's at this school, for students at this school in essence. And the alternative is going to be there is a relationship. There is a relationship between, you can certainly use ditto marks, and the opinion on discipline for students of this school. So another way of wording this would be, there's no association between these two variables. Or there's no correlation between these two variables. That would be the same thing. Or another way of saying this would be that they are independent. No relationship means they are independent. Okay, so that would be the other way of wording this. So the null would be that there is that these two variables are independent. The alternative would be that they're not independent. And then our assumptions are the same as what we just talked about. Our assumptions, conditions, our assumptions, and it just one random sample. So you would say, and you write that sentence out, you would say, it says a random sample is taken, thus random conditions met. We've only got one sample, so you won't have to worry about saying independent random. All right, our population size. So in regards to independence, our population size at least 10 times our sample size. So you need to say there needs to be at least 890 students in this school for our population size, at least 10 times our sample size. And then our expected counts, which we will look at those in a minute, our expected counts be greater than or equal to 5, and I will write those out below, shown below. So you have to write those out. Okay. Now don't say the expected counts are greater than 5, therefore normality is met. No, that is not. That would be counted. That would be counted wrong. So there's your condition. Make sure and write them out correctly. So write out correctly there. And so okay. And so now we do our mechanics, and they are done the exact same way I just described in regards to the expected counts and everything like that. In other words, you get the row total. The row total for the low level students here is 28, and so for the average level, so that would be 48, and so that would be 23, and those should add up to 89, and then you'd add up the total yeses and total nos. The total yeses here is well, I didn't add them up, so That is going to be, let's see, 39 plus 4, that's to be 53. And the total no's is going to be 37 plus 9, which is 46. And so that does add up to 89. So our table total is 89. So remember, to get the expected counts, it would be row total. So for this cell, the expected counts. So for low level, yes. So for low level, yes, the expected count, if you're doing this by hand, would be 28 times 53 over 89. That, in fact, is equal to 14.99. And you would do that for all of the cells. And then you would, with your chi-squared test statistic, you would, calculate chi-squared is equal to observed minus expected squared over the expected. You'd add them up. But I'm going to just go ahead and use the calculator to get these three values. And so this is what we'll do, is we will put all of these values in a matrix. And so here we go. And so I'll do second matrix. Remember, matrix is right above to the x is -1. And so we would go edit. And so we will, so you go to edit matrix A. It is 3 by 2, which, by the way, if you don't enter that right, then your matrix won't come up the right shape. And so we'll enter these numbers, 12 here, 16 here, and then 27, and then 21, and then 14, and then 9. Okay, I believe I've entered those correctly. And so now we'll do our chi-squared test. Of course, the calculator is going to calculate the expected counts for us. So I'll go stat, test, and I scroll down to chi-squared test, which is option C, or chi-squared 2A, A and B. And then we do calculate, and it'll tell me my mechanics numbers there. And so we would say, well, our chi-squared value is equal to 1.923. Our degrees of freedom is 2. Yeah, it would be the row to calculate. That's row total minus 1 times column total minus 1 again. And then our p-value is certainly very large here. And so that's equal to 0.3823. And so there we go. So there is our p-value. And so those are the numbers you have to write in your mechanics. And our ending is the same as it has been for the last several chapters. This p-value is greater than our alpha, 0.05. Thus, I fail to reject. I do not reject. I fail to reject the null hypothesis. Thus, I do not have convincing evidence that, and then you restate your alternative. I do not have convincing evidence that there is a relationship between these two variables. There is a relationship between, in this case, level of student, and opinion on discipline. Discipline for this school. And if you would go back and if you were to look at the components of chi-squared, if you were to go and you were to calculate that in the observed minus the expected squared over the expected, the follow-up analysis, you would get these components for your chi-squared. And so now, of course, we have a really small, our chi-squared value is really small here. It's 1.92. So there's going to be not much contribution. But you would look at this. The one that contributed to it the most would be these two up here, would be the low levels. The low levels for yes and the low levels for no contributed the most. But it's a really small contribution. Anyway, and so in essence, intuitively, what's going on here is, yes, there's a difference in the sample data. In our sample, more of the lower level said no, and more in the average and the advanced said yes, but it's not statistically significantly different. It's plausible this difference is due to sampling variability, even if the null is true and there is no relationship. Okay, so that's it. We're going to have another video to kind of talk about a couple of other little issues that should be much shorter than this one. But thanks for paying attention. I hope you have a great day.